First, who created it and how it was developed. KUBO Robotics is the company behind KUBO. It was founded in 2015 by two Danish engineering students, Daniel Friis Lindegaard and Tommy Otsen. They saw a gap. Younger children in preschool and early primary grades largely are not taught coding or computational thinking in hand-on or playful ways. Often they are expected to use screens or abstract systems before they have the fine motor or abstract reasoning skills. So Lindegaard and Otsen wanted to create something intuitive, tangible, engaging and usable by kids as young as 3 or 4, even before they can read in many cases. They developed a physical programming language, known as tag-tile, where children arrange tiles, physical puzzle-like pieces, which represents commands, instructions, then get the robot to execute them. The development involved collaboration with educators every step, testing prototypes in schools, refining according to feedback. Second, when and how it was invented. The idea was born around 2015, during their time at the University of Southern Denmark. Over the next couple of years they turned the concept into a working prototype. In 2017, they launched a successful crowdfunding campaign on Indiegogo to finance initial production and public interest. Meanwhile, the robot was unveiled publicly, among other events, at CES in 2017. As they tested it more in schools in Denmark and elsewhere, the platform including the physical robot version and digital blended learning versions matured. Over time, extensions like KUBO Hands-On, KUBO Play Digital, and blended solutions were introduced. Third, main features and specifications. Let me clarify. There are two related but somewhat distinct components: the physical robot KUBO with its tactile physical programming, and the digital version, KUBO Play, which simulates similar behavior virtually. Key features include: the robot is screen-free. The child uses physical tiles rather than a screen, helping with tangible learning. Tactile pieces. Different commands like move forward, turn left right, loops, subroutines, functions, parameter tiles, etc. These are combined physically. For the digital side, KUBO Play offers over 100 interactive tasks in 3 modes: free play, open exploration, practice mode, personalized progress, and story mode, connected narrative or challenge-based tasks. Curriculum alignment. The tasks are aligned to K-5 learning standards, elementary grades, and international STEM computational thinking standards. Teachers get lesson plans, guides, etc. As for physical robot specifications, for very young students age 3 to 10 plus, intuitive size, a robot about the size of a drink can in some reports. Battery life, approximately 4 hours of continuous play, with about 1 hour required for full recharge. Components included in starter classroom set: an activity map, 1 KUBO robot, micro USB cable for charging, 46 tactile codes, including movement tiles, go forward, turn left right, loops, function, record, play, parameter tiles. Fourth, body structure and materials used. On this point, the public documentation is less detailed. What is known, reasonably inferred. The robot's outer casing, generally plastic, designed to be durable for use by children. Likely abs are similar, given many educational robots use that. I have not found a definitive public source stating exactly which plastics or composites are used. The head and body connect via simple connectors, only minimal assembly required, head to body before use. Tag tiles are physical tiles, made of durable, probably injection molded plastic, with printed icons. They must be lightweight so children can handle them, yet robust enough to last repeated use. Internal structure. Motors, likely small DC or stepper, for wheel drive, battery compartment, microcontroller, sensor slots. The robot is small and portable, so materials are optimized for weight and cost. Fifth, how it works. Working mechanism, sensors, AI, actuators. The physical robot uses tactile commands. The child arranges tiles on a matter table in sequence, e.g. go forward, turn left, loop, etc. The robot is placed at the start and then executes those commands, moving over or along physical space. It reads the configuration, i.e., which tiles are placed, in what order. The robot likely uses simple optical or contact sensors to detect tile placement, or alternatively the MAT+ configuration has the robot view-based detection. The documentation says, KUBO responds to the command within the tile. There is feedback, lights, sounds, immediate response, which helps children link their physical programming to robot behavior. Sensors. Basic sensors to detect orientation, movement, wheel encoders, obstacle detection. There is mention that the robot should not be used outdoors because water, rain damage it, so it is likely not sealed to IP rating. The Robot Report article states it is not recommended to be used outdoors. On the digital side, KUBO Play, the AI involved is lighter, simulation of behavior, checking correct programming logic, giving feedback, visualizing outcomes instantly, virtual robot on screen. The platform does not appear to employ heavy AI like deep learning, rather it validates code, gives error checking, guides students through standard logic constructs. Actuators. For the physical robot, motors to move, wheels, drives, motors for turns. Also probably small, possibly LED, lights and audio speaker for sound effects. The internal control software, microcontrollers etc., interpret the tile arrangement, translate to motion commands. Sixth, price and estimated cost. When KUBO first launched via Indiegogo, early backers could pre-order a KUBO robot starting at $170. The classroom starter set, one robot plus tag tiles etc. costs more. For example, a KUBO coding starter set classroom set is listed with a price of $1,079 per year for a classroom set. Also, for the digital platform, KUBO Play, they offer subscriptions. For schools, digital school offers begin at €399.20 per year for certain purchasing commitments, and digital classroom offers around €199.20 per year depending on scale. So cost varies depending on whether it's physical hardware, digital subscription, or a blended solution. Also varies by geography, shipping, import duties. Seventh, country of origin. KUBO was invented in Denmark, by founders based at the University of Southern Denmark. The company is headquartered in Odense, Denmark. Eighth, future benefits and applications for humanity. There are several key areas where KUBO and similar educational robots can make distributed, long-term impact. Enhancing early STEM and computational thinking skills. By starting young ages, approximately 3 to 10 children build mental habits of sequencing, logical thinking, understanding loops, functions, conditionals, even if in simple forms, which prepares them for more advanced programming and problem-solving in later education. Reducing inequalities. Making coding accessible even to pre-readers, children in underserved areas, or those without strong teaching infrastructure can benefit from a robot and tag tiles rather than needing advanced computer labs. Encouraging hands-on, physical learning. Many children learn better when they can manipulate objects, see immediate consequences, experiment. This helps retention, creativity, and also increases engagement. Cross-disciplinary learning. KUBO is used not just for coding, but for integrating mathematics, language, music, spatial reasoning. The robot with maps etc. can help in geography, storytelling etc. Impact on teacher training. Educators get new tools, curriculum alignment, ways to differentiate instruction. For society, over time increasing children's familiarity with automation, robotics, algorithmic logic may reduce skills gap, help future workforce adapt better in fields involving automation. Possibly social benefits. Inclusion, e.g. adapting for children with different learning styles, promoting creativity, collaboration, sequencing etc. Ninth, any hidden or less known facts, things not widely publicized or subtle. Although often described as robot and physical programming, KUBO's tag tile is essentially a puzzle-based system. A less known feature is that for many tasks, especially in digital or blended modes, the tile system is simulated. Children lay out virtual tiles, the mapping between code and robot behavior is immediate. This helps when physical robot hardware is unavailable. The digital platform supports regional servers, per recent APK version change, for Android to better serve different geographies. Latency localization. KUBO Robotics has raised multiple investment rounds beyond the crowdfunding, including angel investors in Denmark. The valuation has grown, so the venture side is real. Many people assume educational robots are just small-scale hobby or toy business, but KUBO seems to have serious institutional backing. The designers tested and iterated in real classrooms. Educators had input at many stages, not just after product launch. That contributes to usability, teacher guides etc. While selling globally, the cost of the robot hardware plus shipping, import duties can increase price significantly in some markets. Sometimes digital versions are more feasible for remote or low-income settings. The physical robot's durability depends on handling. Repeated use by younger children can stress connectors or wheels. Some schools report needing spare parts or replacement tag tiles over time. This is anecdotal, but comes up in user forums. 10th, possible future developments and impact. Based on what is known and logical extrapolation, the robot's capabilities may be extended. Perhaps more sensors, obstacle detection, color recognition, touch feedback, possibly even vision to allow more interactive tasks. More sophisticated AI integration. While currently the platform is relatively deterministic, i.e. code right pointing arrow behavior, future versions might include adaptive feedback, suggestion systems, maybe voice interaction or natural language to help guide children. Scaling in digital. More advanced simulations, maybe augmented reality AR to overlay digital stuff onto physical tag tiles or maps, or mixed reality so children can learn coding in physical plus virtual blended environments more seamlessly. Making it more affordable. Cheaper hardware, modular versions, perhaps DIY kits, simplified versions for low-income countries. Expanding the curriculum. Beyond basic coding and computational thinking, more integration with robotics, engineering, AI ethics, perhaps data science for kids, environmental science, etc. Potentially the robot could be used for special education, for children with learning disabilities, adapting interaction to different learning styles. Impact. In the longer term, widespread adoption could shift how early education treats computational thinking, not as a specialist subject but something foundational. Could influence workforce readiness, innovation, inclusion in tech fields. Children growing up with tools like this will be more comfortable with algorithmic thinking, with creating with technology rather than just consuming it. In summary, KUBO Play represents a thoughtful, well-designed educational robot and digital platform, from Denmark, founded in 2015. It blends physical programming, playful design, teacher-friendly curriculum, and digital simulation. While hardware specifications are modest battery, plastic body, simple motors, etc., the value is in pedagogy and usability. The costs are non-trivial for schools, but lower for individual commitments or digital only. And its potential long-term benefits for education, equity, STEM readiness are significant. Hidden features include investment background, regional server support, the survey of classroom feedback, and the scaling challenges.